Welcome back to section 6 of chapter 8. In this one, we're going to look at the three-dimensional Cartesian coordinate system. So our Cartesian system is just our normal graphing system. We're looking at it in 3 dimensions, which is why I changed the background for this one, because in this unit, we're going to be in space. And before we get too much further, I'm just going to apologize right now for the length of this one. I always try to keep them 20 to 30 minutes, but there is a lot of stuff in this topic. Not much of it is particularly difficult, and a lot of it is just an extension of what we do in 2 dimensions. There's just a lot of it. So again, I apologize for the length on this one. Take it in chunks if you need to. But let's get going with learning targets. Our learning targets, sketch points or equations in space, compute distance and midpoint in space, write an equation for a sphere, evaluate expressions using vectors in space, and then solve application problems involving the three-dimensional coordinate system. So we have points, distance, midpoints, spheres, vectors, and then we're going to get into equations of lines and planes using both vectors and parametric equations. So again, there's a lot here. So let's get started.
So the first thing is three-dimensional space. Instead of having just 2 axes, we have 3, which can actually be turned into 3 planes. We've got the x-axis is this one. This is the one that's actually sticking out at you, out off the page. And then the y-axis and the z-axis. Each of them has positive, and then the negative one's going to be back here. Y is positive, negative, z is positive, and negative down there. And so this is similar. We've actually saw this last year in Algebra 2 as well. So if we were to graph a point, we would not actually make all the planes. We would just make the axes that we were using, which would be the x, y, and z. So you'd start out with those guys, and then the x-axis kind of comes diagonal, and then it goes dotted back there. That's where we have it behind the screen, under the desk, things like that. And so this is x, y, and z. If we wanted to graph a point, let's say we wanted to graph the point 3, comma 1, comma negative 2, we would first, let's make the 3, or let's make our tick marks here. Graphing in 3 dimensions is not quite as much of a science as 2 dimensions. It's more of an art form, and it probably won't look perfect. But how we do it, so we're going to always start at the origin. We're going to go 3 in the x direction. So that would be 1, 2, 3. And now we need to move 1 in the y direction. That's this distance, but not starting there. We need to start at where we left off. And so we're just going to move 1 horizontally because the y-axis is horizontal. So we move a distance of about 1. And then 2 negative in the z direction. That's going to be this distance here. So we'd go down 2 that way. And that's where we'd put our point. So that's the point 3, 1, negative 2. The green stuff, like the trails, as I was graphing, that's not part of the point. That does not need to be there. It can definitely help us get to the right-ish spot. And it's also kind of like showing your work. So if you want that there, that is perfectly fine. But it doesn't have to be there. It's not part of the point. Now, what's weird about 3-dimensional graphing, especially if we don't have that trail there, is that this is not the only point that could be in that exact spot. This also looks like it could be x is 5, y is about 3, and z is 0. In fact, there's an infinite number of points. Like even if you graphed it perfectly on this two-dimensional surface, there's an infinite number of points that would look like it's at the exact same spot. Basically, the line of points going from that point through your eyeball could all be graphed at about that same spot. So that's 3D space, that's graphing in 3 dimensions. The 3D space is also broken up with 2 dimensions. The axes break the graph into 4 quadrants. And we know these. This is quadrant 1, 2, 3, 4. Well, for 3 dimensions, we have those extra axes. It breaks it up into 8 pieces, which are called octants. So the 8 octants would be these ones. Now, they actually go in basically the same order as the quadrants. Octants 1, 2, 3, 4 are the same thing as quadrants 1, 2, 3, 4, where z is positive. Octants 5, 6, 7, 8 are the same as 1, 2, 3, 4, except z is negative. So like quadrant 1, x and y are positive, z is positive. Quadrant 2, x is negative, y is positive, z is positive. And then etc. Quadrant 7, they're all negative. And so sometimes it'll ask what quadrant it's in, and you can just see those. And again, it's the same as or what octant, it's the same as the quadrants, except that z is positive or negative. Distance and midpoint formulas. Just because we're in 3 dimensions doesn't mean we don't have distance and midpoints. The nice thing is if you had to take the 2-dimensional ones and turn them into 3-dimensional, chances are you would come up with exactly the same thing. So, midpoint for 2 dimensions. We find the average of the x's, the average of the y's. We were doing this even just last chapter. If we had the endpoints of a diameter of a circle, we'd have to find the center. And so looking at this, if we had 2 points, let's say 3, 7, and 5, 12, the midpoint, we'd go 3 plus 5 is 8, divided by 2 is 4. And that should not be a surprise that 4 is halfway in between 3 and 5. When we have something like 7 and 12, it's a little bit more difficult. 7 plus 12 is 19, divided by 2 is going to be 19 halves, or 9 and a half, which is a little bit harder to just kind of eyeball and know that, oh yeah, 9 and a half is right in between 7 and 12. That's why the formula kind of works out. So that's 2-dimensional. If we want 3-dimensional, we do the same thing, we just have z as well, because we have that ordered triplet instead of an ordered pair. So if we have a couple points, let's say 2, -1, 7, and 8, 3, 2. We're going to do the same thing. 2 plus 8 is 10, divided by 2 is 5. -1 plus 3 is 2, divided by 2 is 1. And 7 plus 2 is 9, divided by 2 is 9 halves, which could also be 4 and a half if you wanted to go that way. But that would be the midpoint between these 2 points. So it's the exact same thing you do with 2 dimensions, except you have to do it with the z as well. Distance works out basically the same. The distance formula, x minus x squared plus y minus y squared, big square root. Same thing, except we also have the z's in there as well. So let's find the same, use the same points. Let's go the distance here. So we'll have a square root. We'll have a 8 minus 2 squared plus 3 minus -1, which would be 3 plus 1 squared, plus 2 minus 7 squared. And the nice thing about this is it doesn't matter what order you're in. You can even switch the orders because the only thing that's going to change is the that sign. When you square it, it's all going to be positive anyway. So it makes it even harder to mess up. 8 minus 2 is going to be 6 squared, plus 3 plus 1 is 4 squared, plus 2 minus 7 is negative 5. When we square it, it'll be positive anyway, so we'll just go 5 squared. That way you don't do something horrible like putting negative 5 squared into your calculator and get negative 25, because we all know that that's not good. 6 squared is 36, 4 squared is 16, 5 squared is 25. We can add these together. 36 plus 16 is 52, plus 25 is 77. So we get the square root of 77. Very frequently, these will not simplify down to a nice whole number. Sometimes they do, sometimes they don't when we have just regular distance in 2 dimensions. Rarely will these simplify to a whole number in 3 dimensions. It is possible to simplify it a little bit, but not in this case because this is 7 and 11. They're both prime, so that is where it is. Next piece, standard form of the equation of a sphere. I really could have faded this in now that I'm doing the retake on this, but I forgot to do that, so it will sit there and wait. Let's see if I can remember to do it before going on to the next slide this time, however. So, equation for the standard form for the equation of a sphere. Just like everything else, this is a direct extension of 2 dimensions. 2-dimensional, we have a circle. The equation of a circle with a center at hk and a radius of r is going to be x minus h squared plus y minus k squared equals r squared. We just got done doing that last chapter. So for a sphere, we're going to center it at hkj. Why do we use j? Because it's the letter that comes after k. The radius equals r, and so it's going to be the same thing, x minus h squared plus y minus k squared plus z minus j squared equals r squared. One of the mistakes people make on this is they try to go with a cubed on something. It's all squared. The sphere, it's not like a solid ball, it's only the outside. It's an area type thing, so it's squared. If we did want the whole thing all the way to the center, like the Earth is a sphere, we want to consider the whole Earth and not just the crust, we'd go, it's all less than or equal to r squared. And that would get us everything. When we get volumes, that's when we get cubes. So that's a sphere. If we wanted to write the equation, if we had a center and a radius, we just plug it right in. But more exciting, find the center and radius of the sphere. In order to do this, we're going to have to write the equation of the sphere, and then it'll be right in the equation. So how do we change this into the equation of a sphere? Oh, did someone say completing the square? Yeah, you know that thing we worked on a lot last chapter? It's still here. The nice thing is it's still exactly the same. So let's complete the square here. We're going to start out by grouping the x's, the y's, and the z's. So we'll have 2x squared minus 2x, and then leave a space, plus 2y squared minus 6y, leave a space, plus 2z squared minus 4z, and then we'll move the 5 over to the other side. Oh, we need to factor out those 2's. So, fun story, if you are doing other conic sections, they also translate exactly just like the circle does to the sphere. You get ellipsoids. Those are really nice, super easy, like it makes sense. The hyperboloids and paraboloids are, the equations translate perfectly, but they're a little bit tougher to like imagine in your head. But the ellipses, though, perfect translation there. So we're going to factor out the 2. So we have 2 x squared minus x, leave a space, plus 2 y squared minus 3y, leave a space, plus 2 z squared minus 2z, leave a space, equals -5. Now we can complete the square, so we'll have 2 times something squared plus 2 times something squared. Well, this will be an x, this will be a y, plus 2 times z something squared will equal something. I don't have much space over there. We'll figure that out. So, first one, the x's, we divide by 2. Well, that's -1, so that'll be a -1/2 squared. It's plus 1/4. We have to add to the other side, but we don't add 1/4. It's 2 times 1/4, which will be plus 1/2. For the y's, -3 divided by 2 is -3/2 squared plus 9/4 times 2 will be plus 9/2. And then for the z's, divide by 2 is -1, so that's plus 1 times 2 is plus 2. We had that -5 up there. I'm just moving it down because I don't have the space off to the side. -5, so 1/2 plus 9/2 is 10/2, which conveniently is 5, plus -5 is 0. So that makes this equal to 2. Almost done, but we don't want these 2's, so we're just going to have to divide everything by 2 to get x minus 1/2 squared plus y minus 3/2 squared plus z minus 1 squared equals 1. And so our center, because that's what the question's asking, center and radius, center would be 1/2, comma 3/2, comma 1. And the radius equals the square root of 1, which is 1. So that's how we can find the center and the radius and just write it in standard form. It's the same thing we've been doing all last chapter. Finally, the trace of a surface. Now, a trace of a surface is where we just take one little cross section. Generally speaking, when we will do it, it'll be on one of those planes, like the XY plane, the YZ plane, the XZ plane. So it'll be on one of those, and it's just where does it intersect that plane. So it's kind of like an intersection. In fact, that's also how we find it. So to do this, we're going to sketch the XY trace of the sphere given by x minus 3 squared plus y minus 2 squared plus z plus 4 squared equals 5 squared. So the XY trace, that's going to be on the XY plane. What every point on the XY plane has in common, z equals 0. On the YZ plane, x equals 0. On the XZ plane, y equals 0. Whatever one is not here will equal 0. So all we're going to do is we're going to plug this in and then simplify. So we'll have x minus 3 squared plus y minus 2 squared plus 0 plus 4 squared equals 5 squared, which is 25. These aren't going to change. Just x minus 3 squared plus y minus 2 squared plus 4 squared is 16 equals 25. Subtract it over. X minus 3 squared plus y minus 2 squared equals 9. So this would be a circle with a center of 3, 2, and a radius of 3. To sketch it, we would have our axes. I don't have enough room here. I'll actually show you a good picture of this as well. Then we're going to start out with our center, 3, 2, 1, 2, 3, 1, 2. The center will be about here. And then we'd go over 3, over 3, over 3 this way. It'll take us about there. Over 3 here. And then we make our circle. If my pen would actually work here. Oh, There it goes. It all came at once. Um, and so that's kind of what it looks like. It's on there. Now, what does it actually look like? We have a sphere, and we're just taking this cross section where it's right here at the, right there at that plane, and that's the part that we're looking at. So, most of this stuff, again, is just an extension from what we've been doing. A lot of it we've actually seen before, but not necessarily this year. So, this is the first topic of the 4. Until next time, keep working problems, keep asking questions, and as always, happy mathing. So the very first thing we're going to look at is the component form. In 2 dimensions, that was just this. Remember, a vector looks kind of like a point, except that it uses the angle brackets instead of parentheses. So an example here could be v equals 1 comma -4. That's a vector in component form. For 3 dimensions, it's the same thing, except there's 3 things. Just like with a point in 3 dimensions, there's 3 points because we have the x component, the y component, and the z component. So our vector here could be 1, -4, 7. I mean, it's just whatever it is. And remember, that's like how you get from the first point, the initial point, to the terminal point, which is the ending point of the vector. We have the unit vector form as well. That was the form that involves the I and the j, where I is the x component, j is the y component, and then we just change it so it makes it a sum instead of using the brackets. So, for example, if we use the exact same vector that we had up here, it would be v equals 1i. You wouldn't usually put the 1, but whatever, minus 4j. Same thing with 3D, except we have I, j, and k. Why do we use k? Because it's the letter that comes after j. And so it would expand out the exact same way. And so our vector, the same one we had up here in unit form, v would be 1i minus 4j plus 7k. And so, I mean, you can translate it back and forth between them. It's super easy. A lot of things, component form works better, but some things, the unit vector form works better. And so it's just nice to be able to use both of them. Next piece, the magnitude. If you remember the magnitude, that's the distance, the length of the vector. It translates in word problems. It could be the power, the speed, a lot of things. But as far as the graph actually goes, it's the length. And so it's just distance formula. It's the x component squared plus the y component squared, and then square root. So if we have our vector v is 3, 5, the magnitude of v, and the hardest part about magnitude, remember, is knowing what it's asking. So many people just give me a absolute value. It's not an absolute value. It's the distance. Anyway, so it'll be the square root of 3 squared plus 5 squared, which is the square root of 9 plus 25. So the magnitude of v equals the square root of 34. Same thing for 3 dimensions, except we have 3 pieces to it. So if we have our vector is -1, 3, -2, the magnitude is going to be the square root of -1 squared plus 3 squared plus -2 squared. Now remember, when you're doing this, the negatives aren't going to be a factor because when you square them, they will be positive. don't blindly put them into your calculator and get things like -1 and -4. Don't do it. Don't be that guy. So when we do this correctly, we'll get the square root of 1 plus 9 plus 4, which is the square root of 14 would be the magnitude of this one. Next piece, a unit vector. Not the unit vector form, as we saw on the last slide, but an actual unit vector, a vector of length 1 going in the direction of the vector that we have. In order to get this in 2 dimensions, we just took the vector and divided by the magnitude. So if we use the same one that we just had, our unit vector would be 3 over root 34, comma, 5 over root 34. That would be the unit vector. If we found the magnitude of this, it would come out to be 1, and it goes in the exact same direction as our original vector v. Well, in 3 dimensions, it's actually the exact same thing. It's the vector divided by the magnitude. If you wanted a unit vector in 4 dimensions, it would be a vector divided by the magnitude. So that doesn't change because the equation doesn't specify what the size of the vector is, unlike, say, the equations for magnitude. We only have 2 things, we have 3 things. And so the unit vector for this one, we're going to have -1 over root 14, comma 3 over root 14, comma -2 over root 14. And that's finding the unit vector, a unit vector in the same direction as a vector. You find the magnitude, divide by the magnitude. Next piece, sum of vectors. If we remember 2-dimensional, we just add the x component, add the y component. Super easy. So if we have u was -2 comma 4, and v is, say, 3 comma 7, u plus v is going to be -2 plus 3 is 1, 4 plus 7 is 11. Super easy. We just add these two together and add these two together. In 3 dimensions, same thing, only we have 3 pieces to it. So if we have u equals 3, 7, -4, and v equals -1, 6, -5, u plus v will have 3 plus -1 is 2, 7 plus 6 is 13, -4 plus -5 is -9. So we can add our 2 vectors together. It's the exact same thing we did for 2 dimensions. We just have that third piece in there. Scalar multiples, same idea. If we have something times a vector, we just distribute it through. So let's say we use the same u from up here. U was -2 comma 4, and we wanted 5u. We would just distribute. 5 times -2 is -10. 5 times 4 is 20. 3 dimensions, same thing. We just have to distribute to all 3 pieces. So if we take, say, the same u, and we want to multiply by -2, let's go -2u. Well, that's going to be 3 times -2 is -6. 7 times -2 is -14, and -4 times -2 is 8. So there's -2u for our 3-dimensional vectors. Again, it happens exactly like the other things. Now the scalar multiples is going to come back in a couple more slides because we're going to use those to figure some other stuff out as well. But first, dot products. The dot product is one of the forms of multiplying. We're actually going to find the other form of multiplying in the next section, or perhaps the fourth section. But the dot product, we take the x components, multiply, take the y components, multiply, then we add those together. So if we had, say, u was 2, 5, and v is 3, -1, u dot v, v not 5, is going to be 2 times 3 plus 5 times -1. 2 times 3 was 6, plus 5 times -1 is -5. So u dot v, in this case, would equal 1. Notice this is a scalar, this is a number, this is not a vector. The dot product returns a scalar, or a number. In 3 dimensions, same thing, except we have the z ones we have to multiply and add in as well. So if we say u equals 3, -1, 4, and v equals 2, 7, 3, then u dot v is going to be 3 times 2 plus -1 times 7 plus 4 times 3. I wouldn't normally write out this step. I'd go 3 times 2 is 6. And so I'd write out this next step. We'd have 3 times 2 is 6, minus 7 plus 12 is going to be 11. So that's the dot product, which is, again, a scalar. It's something that is used in a few things, specifically finding the angle between the vectors. So now the angle between the vectors in 2 dimensions and 3 dimensions, just like the unit vector, the equation is the same. So the cosine of the angle in between them is going to be u dot v divided by the product of the 2 magnitudes. So we'd have to find the magnitudes here because we have our dot products for each of these. So we'll use the vectors that we have, find the magnitudes. So here, magnitude of u is going to be the square root of 2 squared plus 5 squared, which is 4 plus 25, which is 29. Magnitude of v will equal the square root of 3 squared plus 1 squared, which is 10. And so here, the cosine of our angle in between them is going to be u dot v, which is 1 over root 29 times root 10. So root 29 times root 10 is going to be some horrible, horrible decimal. Root 29 times root 10. It's going to be 17 point something, blah, 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 blah. We want 1 over that is going to be about 0.0587. So cosine of that is going to be about 0.0587. And then if we want to find the angle, we would do the inverse cosine in radians or degrees, depending on what the problem is asking for. A lot of word problems are going to be in degrees, just because that's what we're used to using more often. So we'll find it in degrees. So we'll go inverse cosine of our answer to get 86.63 degrees. So make sure that you can do this as well. If you have a calculator at home, awesome. Even a scientific calculator can do this stuff. If you don't, but you're using your computer, the TI website is offering a lot of their software for free for the next 6 months because of the situation we're in. So if you go to education.ti.com, you can get some really cool software to play around with for the next few months. All right, so that was 2 dimensions. We've done that. All right, 3 dimensions. First thing we're going to need to do is figure out what our magnitudes are. So we'll have the magnitude of u will equal something. So we have 3 squared plus 1 squared plus 4 squared. That's 9 plus 1 plus 16, which is 26. And we'll have the magnitude of v, which will be the square root of 2 squared plus 7 squared plus 3 squared. That's 4 plus 49 plus 9, which will be 62. So we have the square root of 62. So we can set it up. Cosine of our angle equals the u dot v, that's the 11. We've already found that, over root 26 times root 62. So we can figure out what that is. I always do the roots first so that I don't accidentally do like 17 divided by root 26 and then multiply that by root 62. So we'll go root 26 times root 62 equals that. We're going to go 11 divided by that number. Gives us about 2.739 or 2.7397. So cosine of our angle here is about 0.27397-ish. I'm not going to use that number. I'm using what's in the calculator. Just like we always have, inverse cosine of that gives us 74.099 degrees. So let's say 74.1 degrees. So that's how we can find the angle between the two vectors. It's the same as we did in 2 dimensions a couple chapters ago. Next, we use parallel vectors. Vectors are parallel if they are scalar multiples of each other. So if we have in 2 dimensions, if we have the vectors 2, 6, and the vector, let's go 6, 18, this one is going to be 3 times 2, 6. So it's a scalar multiple of it. They are parallel. They just have different magnitudes, but they're going in exactly the same direction. One way of finding this, like here it was pretty easy. It's like, oh, well, that's multiply by 3. If you take the x components and divide them, and then the y components and divide them, if you get the same number, then they're parallel. So for 3D, same exact thing. It's just all 3 of them have to work out. So if we have 1, 7, 4, and we have, I won't make it too complicated here. Let's go 5, 35, 20. Hey, this is just going to be 5 times 1, 7, 4. So these two would be parallel. Again, if you can factor that out, they're parallel. If you can't, then they are not parallel. It has to work for all of the pieces of it. Collinear points they're collinear. They're in the same line if the vectors between any 2 of the points, usually you're going to have 3 points. If the vectors between them are parallel, or they're scalar multiples of each other, then those points are collinear. So you would have 3 points. So let's say for 2 dimensions we have the point 1, 3, the point 2, 5, and the point 4, 9. We can find any 2 vectors, either like the first and second, second, third, first and second, first and third, doesn't matter, any two vectors. So let's find these two. To get from 1 to 2, that's going to be 1. 3 to 5 is going to be 2. And then these ones, 2 to 4 is going to be 2. 5 to 9 is going to be 4. Hey, this one's just 2 times 1 comma 2. So these 3 points are collinear because the two vectors are parallel to each other. For 3 dimensions, same exact thing. We'd have 3 points. So I don't know, negative 2 comma 1 comma 4, 3 comma negative 2 comma 9, and 13 comma negative 8 comma let's go 15. So we can find our vectors here. This vector from negative 2 to 3 is going to be 5. From 1 to negative 2 is negative 3. And from 4 to 9 is 5. This one from 3 to 13 is going to be 10. From negative 2 to negative 8 is negative 6. And from 9 to 15 is 6. So in this case, this is 2 times 5. This is 2 times negative 3. But this one doesn't work. So these ones are not collinear because they're not scalar multiples. Like 10 divided by 5 is 2, negative 6 divided by negative 3 is 2, 6 divided by 5 is not 2. Doesn't matter what it is not 2. So that's how you can tell if they're collinear. Again, it's just scalar multiples. It's the same idea as parallel. And finally, we have terminal points. So a terminal point, if you have an initial point and a vector, find the terminal point. You just add the vector to the initial point. So kind of like what we were doing right up here to find the vector. So from 1 to 2, that was 1. From 3 to 5 is 2. It's actually subtracting. 2 minus 1 is 1. 5 minus 3 is 2. These ones are going to be more if we have an initial point of 2, 7, and the vector is 1, negative 3. What is the terminal point? Well, we would go 2 plus 1 is 3, and 7 plus negative 3 is 4 to get the terminal point. Same thing with 3 dimensions. If we have the initial point is 0, negative 1, 5, and the vector is 7, negative 2, 4, that's a vector, then the terminal point would be 0 plus 7 is 7, negative 1 plus negative 2 is negative 3, 5 plus 4 is 9. So, I mean, finding the terminal point is pretty easy. You could also, if you had the terminal point, you could go backwards and find the initial point by subtracting. And so that's a pretty straightforward, not too hard thing. But notice everything we did was basically the same as in 2 dimensions, which we did a couple chapters ago. So there's not really anything new here. Chances are, if I just gave you the stuff, you could have had most of it figured out about 25 minutes ago without ever having to listen to me. But where would the fun in that be? So, as you're working on this, remember to always keep working problems, keep asking questions, and as always, happy mathing. Until next time. So first we'll look at lines in space. Now, To write the equation for a line in space, we use what's called a parametric equation. And what a parametric equation is it defines each of your variables by using an extra variable. We'll see what that looks like in just a second, but instead of having like one equation for the line, it's going to be a set of equations. One equation will be for the x value, one equation will be for the y value, one equation will be for the z value. So, for an equation of a line, anytime we write the equation for a line, we need two things. We need a slope, and we need a point. Well, the slope in 3 dimensions, what really talks about a slope and what we've been talking about is a vector. So we need a vector that it's parallel to, because this is what gives us our slope. And what's nice here is instead of vector v being v1, v2, v3, it's just a, b, c. We only really deal with one vector at a time, so we can have just a, b, and c. And for a point, there's x1, y1, z1, as opposed to the variable x, y, and z that we will see. So this x1, y1, z1 is similar to the point in a line where we have x1 and y1. So we have a slope, and we have a point, and that'll give us the equation for the line. So the equation, x will just be the x point plus a, the x part of the slope, times t, and that's that extra variable here. And I'll mention what that does in just a second. So, but x is just x1 plus a times t. Y is y1 plus b, the y part of the slope, that y part of the vector, times t. And z, as you could possibly guess, is z1 plus c times t. So, this t value, what does this do? We can pick any number we want for t and plug it into each of the equations, and that will give us a point on the line. So for example, I don't have an equation yet. We'll do this when we have an equation, but we could use when t equals 1, and we plug in 1, and we get a point. And we can put t equals 2, plug in 2, and we get a point. We can put t equals -7, plug in -7 to each of them, and we get a point. So we have the equations of lines. With that t, we can solve for t for each of them. So, for example, x, we'd subtract the x1 and then divide by a. And we solve for t for each of them. T will always be the same for each of the 3 parts of our point. And so what we get is what's called a symmetric equation, which we just solve for t for each of them, then we can put them equal to each other. And that equals t. Is that hugely useful? Not particularly. It has some uses. And like other equations like this where we have 3 pieces, we would only actually use 2 at a time. So let's find the equation of a line. Now, if we have parallel to v, like we have our vector, we have our point, you just plug it in. That's boring. Let's do a line through 2 points. Let's do a line in space through, let's have the point 1, 3, -4, and -2, 7, 1. So the first thing we do is we have to find that vector v. Vector v is going to be going from one of the points, sorry about that, excuse me, one of the points to the other point. It does not matter which way we go. All that will do is change the a, b, and c to negatives, and being that we could put either a negative or positive t in, it becomes the same thing. So let's just go from the top point to the bottom point. So to get from 1 to -2, we would subtract 3. To get from 3 to 7, we'd add 4. And to get from -4 to 1, we would add 5. So there's our v. Now for our point, we could pick either of the 2 points on the line. It does not matter which point. We will get the same points, we'll get the same line, but the equations will look different. Same thing as if we had gone the other way for the points. The equations would have a negative instead of a positive. But that's okay. The equations can look different. It will still get us the same series of points for the values of t that we would plug in. So let's use the top equation. So here we get x will equal 1 minus 3t. Y will equal 3 plus 4t. And z will equal negative 4 plus 5t. Now if we plug in 0, we get that first point. If we plug in 1, we get that second point. If we plug in 2, so when t equals 2, we get the point 1 minus 6, which would be negative 5, 3 plus 8, which is 11, and negative 4 plus 10, which is 6. So we could plug in t equals 2, we could plug in t equals negative 1, we could plug in any value we want for t, including decimals and fractions. And so we get those. That's how you deal with lines. Again, it's this set of parametric equations, which uses this extra variable to define each of our three variables. Oh, a, b, and c can't equal 0 for obvious reasons here. All right, so now planes in space. With a plane, we don't use a parametric equation for a plane, but we get one equation that will have x, y, and z. So to find a plane, the equation of a plane, we need a point on that plane, which is x1, y1, z1, and we need a vector, because that gives us some sort of a direction, and we call this a normal vector. So you might be thinking like, well, what vector to use? Because there's a ton of vectors that could be on a plane. I mean, you think about like a piece of paper, like just a regular plane, you can draw a line any direction on that. This is true. So instead of using a vector that's actually on the plane, we use the vector that is orthogonal to the plane. So it's one that's coming out at 90 degrees from the plane. There's one vector that will do that, plus scalar multiples of that vector. And so that's what's called the normal vector, and that we're going to call ABC, just like we called the vector for the lines. Kind of strange. So now to make the equation of this plane, we can have it in standard form, where we take x minus the x point times a, and y minus y point times b, z minus z point times c. So if we have a normal vector, n is 3, 2, 7, and it goes through the point 1, 5, 6, we can make this equation. It's going to be 3 times x minus 1 plus 2 times y minus 5 plus 6 times, nope, 7 times z minus 6 equals 0. So that's the standard form of this equation. Now, depending on what point we chose on the plane, the equation could look different. And so we also have what's called the general form. And what the general form is, just ax plus by plus cz plus d equals 0. All we do is we multiply this out and then combine our constants. So this will, if we do that, we'll have 3x minus 3 plus 2y minus 10 plus 7z minus 42 equals 0. And then negative 3 minus 10 minus 42 is negative 55. So we get 3x plus 2y plus 7z minus 55 equals 0. And this will be the general form, whereas this top one was the standard form. So when you have a normal vector and a point, it's really easy. If you have a 3 points, any 3 points that are non-collinear, so they can't just fall in a line, they will define a plane. So if you have any 3 points, we could actually find this. So let's take 3 points. Let's go, well, let's start with 0, 0, 0. We'll make this one a little bit easier here. 0, 0, 0, 2, 1, 7, and 3, 0, -1. So if we graph this, and we would make a triangle, we need a point. Well, we have 3 points, so that's taken care of. And we need a normal vector. Well, we don't have that, so we need to find it. The normal vector is orthogonal to the plane, so we need to find a vector that's going to be orthogonal to this plane. How are we going to do that? If you're thinking to yourself, wait a second, I know this, we just did this, you are correct. To find a normal vector, we find a cross product. So we're going to need 2 vectors out of this, and just like with the area of a triangle that we had in the last section, we just need to start from one of our points and go to each of the other 2 points from that point. So I'm going to start from 0, 0, because that makes one of the vectors 2, 1, 7, and the other one 3, 0, -1. Because starting from 0, 0, that's where we go. So we can do the cross product of this. So we're going to have the determinant. We'll have an I, j, and k. And then 2, 1, 7, 3, 0, -1. We'll extend this. Do the positive ones. That's going to be a negative I. 3 times 7 is 21j. 0k minus, go this way now, 3 times 1 is going to be 3k. That was a horrible k. 0i and minus 2j. So combine our like terms, but before we do that, let's go ahead and distribute this negative so we don't look like a fool. Alright, now we can combine our like terms. We have a negative I and a 0i, so that'll be a negative I. We have 21j plus 2j is plus 23j, and 0k minus 3k is minus 3k is the cross product, which means our normal vector, n, is -1, 23, -3. Now for the point, we can use any of the points. I am going to choose to use the point 0, 0, 0 because I like doing things the easy way. So we just need to plug these in. We'll have -x because minus 0 plus 23y minus 3z equals 0. When you don't have that d term, when you don't have that, it means that it goes through the point 0, 0, 0, by the way. So that's the equation for the line. If we had chosen any of the other points, that d term would have ended up canceling out. So this general form of the equation would always be the same no matter which point we chose. And so that's some planes in space. We have equations of lines, we have equations of planes, and that's about it. So I will catch you later. Until then, keep working problems, keep asking questions, and as always, happy mathing.